Ecco, questo è un meeting, diciamo, quasi formativo, perché il convegno è quello di domani sulle smart media e mobile health e Biodevices, che sarà al CNR in presenza, ma anche in webinar domani mattina in particolare, e poi nel pomeriggio ci sarà una tavola rotonda sull'osservatorio tecnologico per la disabilità. Questo è un po' il programma delle 2 giornate e oggi volevamo appunto fare una specie di tutorial, un seminario per chi ci vuole, che ci ascolta, facendo un po' un confronto di alcune esperienze nell'uso della sensoristica e delle tecnologie smart media in campo medico, ovviamente. Quindi l'IoT, l'Internet of Things, tutto il vario campo della sensoristica. Teniamo presente che quest'anno si terrà in Italia la Eurosensors, il convegno europeo di sensori sulla sensoristica applicati in tutti i campi dello scibile umano, a Lecce a metà settembre. Quindi vogliamo focalizzare tra oggi e domani con esperienze anche interessanti di alcune start-up che stanno nascendo, anche grazie per esempio alla Bicocca e altre ditte che si stanno creando sull'applicazione dell'IoT in campo medico, che possiamo definirlo come Internet of Medical Technology, IoT, things, l'internet delle cose applicate o dei dispositivi applicati in termini in campo biomedico, con tutte le implicazioni anche di carattere legislativo, privacy, sicurezza dei dati, la capacità di questi sensori di essere mantenuti e quindi di garantire questa capacità di garanzia del dato che rilevano alla piattaforma poi informatica lungo la linea della rete, che in questo caso potrebbe essere anche internet, se non sono reti dedicate, reti virtuali private per esempio. Il problema grosso è quello avere a livello di monitoraggio e di riabilitazione, di telemedicina, avere che i dati che provengono acquisiti direttamente dal paziente o a distanza o sul suo corpo abbiano la qualità nel momento in cui vengono raccolti, cioè che non ci sia dispersione lungo il tragitto, lungo la telecomunicazione. Questo è uno dei meccanismi importanti per evitare di incorrere in false diagnosi o in falsa interpretazione, e quindi la diagnosi poi non è accurata come quando invece un medico acquisisce direttamente da vicino questi dati. E questa è una delle critiche che vengono fatte dai medici, ma siamo sicuri che il dato che arriva alla piattaforma, che arriva a me sul mio video, sul mio portale, è il dato veramente misurato da questo sensore. Quindi voglio una garanzia, voglio addirittura c'è un po' di scetticismo nella telemedicina da parte di una frangia del corpo sanitario. Noi dobbiamo fare in modo come tecnologi di garantire questa qualità, magari che ne so, se c'è questo scetticismo, con webcam, far vedere che realmente lo strumento è applicato al paziente in quel posto giusto, al cuore, piuttosto che a seconda della patologia che stiamo trattando, o nella mano o nella coscia, se è un accelerometro, o in altre parti del corpo, in modo da rilevare in maniera corretta e sicura questi dati. Ecco. Si potrebbe pensare nella teleassistenza domiciliare anche di dotare il paziente, già ci sono applicazioni, di dotare di una videocamera in grado di dire all'infermiere, all'operatore sanitario, al medico a distanza che realmente il dato viene preso al posto giusto su quel paziente, su cui fare poi la valutazione sullo stato di salute del paziente, sull'evoluzione della sua malattia o meno. Questo è importante, e quindi discuteremo tra oggi e domani anche applicazioni, ma anche questioni di carattere tecnologico e amministrativo legale, perché il tutto funzioni e questa piattaforma di telemedicina, queste piattaforme di telemedicina, di telemonitoraggio, di teleriabilitazione possono essere perfette, diciamo buone e accettate dal mondo sanitario. Questo è un po' l'obiettivo nostro, per facilitare la loro attività, per migliorare, per aumentare una platea di pazienti da osservare, da curare, da monitorare e da seguire nei follow-up. Un po' il nostro ruolo è quello di garantire che queste piattaforme, anche intelligenti o meno intelligenti, siano in grado di cooperare con il servizio, le attività di carattere rutinario che poi gli operatori devono prendere, devono attivare. Quindi ormai sono oggetti sempre più presenti, dobbiamo governarli, dobbiamo usarli al meglio. Questa era un po' l'introduzione. Matteo, a te.
Yeah, thank you, Francesco, and for this clear introduction. It's a pleasure for me to chair this session in this event of today that introduces the Congress of tomorrow. As you perfectly say, the main topics are passing through the data reliability in medical informatics and digital health. Also the topic of digital divide, that on an international scale is very important because it impacts on the goodness of the diffusion and the reliability of the medical digital informatics services. And so, of course, I think that our first speaker today, which is Professor Giancarlo Mauri, is one of the most skilled person in Italy that could talk about this, introduced in our session. So please, I'm giving the talk to Giancarlo Mauri, professor in the Bicocca University of Milan. So, is Professor Mauri.
Okay, thank you. But now I have to share the screen. Francesco, it's his introduction as yet speak of Internet of Things and Internet of Medical Things. Internet of Things is one of the current frontiers of technology, and inside the Internet of Things, the application to the health problems, to the health systems, have a special and specific role, because there are specific needs of the patients, and as Francesco has yet talked about, there are real problems of quality of data and of decisions that we take on the basis of this data. So, Internet of Medical Things is a specific part of the Internet of Things, and sensors have obviously a very relevant role, because the other current technological advances are in artificial intelligence, and artificial intelligence algorithms are hungry of data. And devices, medical or also domotic devices in general, are a source of a big quantity of data, big amount of data that can be fed to the artificial intelligence algorithms. And so what I want to speak about is that the systems of Internet of Things have a general architecture, okay, and they have there are 4 steps essentially. There are sensors that collect data. Then this data must be collected and communicated to servers, to the cloud, and so where data can be analyzed to give support, decision support essentially, and to then feed other devices, maybe that are actuators or human medical specialists, for example, that have to take actions in this case. So I want to talk about a project that I've of what I was responsible 2 years ago. This is not the project to develop products, specific products or services, but the idea was to build a sort of neutral terrain where companies can act not as competitors, but they can interact so as to stimulate co-fertilization among the different subjects. And so to test new technologies, new approaches, and so on. This was based on a laboratory built up by my university, University of Milano Bicocca, to develop a prototypical solution of Internet of Things through the collaboration between the different stakeholders that are the providers of technological infrastructures and tools, and small and enterprises interested to develop specific products or services. The first phases, the project involved with 2 universities, Milano Bicocca and Pavia, ST Microelectronics as provider of devices and of hardware tools, and some small enterprises for ESCOM technology for communication technology, Alexis and TechInnova essentially for integration of work. And in order to, it's not can you see here? I want to present the use cases we focused on. This just to try this cooperative approach. The use cases were in the area of active aging, with the main idea of offering services to support active aging and for intelligent assistance to elder people and to their families. In particular, to the realization of a client-server system for healthcare and safety assistance, remote system. The main functions of these systems should be to recognize signals, early signals on that can be related to critical physiological conditions, and hence to recognize if a person with a chronic disease has a situation of a risk situation, and in general to monitor the health states of persons and predict anomalous situations in this. And we individuated two main domains of use. One is indoor, and the second is on the car, in automotive domain. So you can see you have looking at the mirror, you can fall down and so on, or you are looking at the TV. And so there are different sensors, cameras, proximity sensor, Fitbit, or ambient sensors, and that collect data on your status or your activity and so on. And the same inside your car with this the same kind of sensors. This is we defined a set of possible scenarios of this. In this case, you see there are two old people, elder people that can have wearable or not wearable sensors for cognitive and physical state estimation, heart rate, electrodermal activity, breathing rate, and maybe other. There is a TV with a camera, including an artificial intelligence assistant for person behavior logging, action recognition, gesture recognition, multi-person interaction, anomaly detection, and sort biometric. And all this analysis activity based on machine learning algorithms can be in part done locally, directly. We can, particular ST Microelectronics was interested to develop chips with intelligence machine learning algorithms on the chip. There are obviously problems of power consumption, because this is true for every kind of device, because you cannot be cannot have to change the battery or to recharge the device every 2 hours. So the power consumption considerations are fundamental for this kind of devices. Okay. Or you are in front of a mirror, and even in this case, the sensors can collect data and then analyze them for cognitive and physical state estimation. And one of the prototypes we developed was a smart magic mirror able to, based on face description, emotional state logging, and so on, to recognize the states of the person. And the general architecture was to have 3 levels, sensors that collect data. Sensors can be with CPU or without CPU. In this case, part of the elaboration of data analysis can be done directly by the sensor. Otherwise, the data are sent by Bluetooth to a concentrator, to a gateway, and then to the cloud through the to the internet, or even through radio connection if you don't have internet available of low connection. So the idea, as I said, was to experiment different approaches and different technologies. And this, okay, so sensors, you can have imaging sensors or sensor to collect biometric data, or ambient sensors. Some of them have a CPU, miniaturized CPU, able to execute intelligent algorithms to analyze the signals that came from the sensors and to give a compact metadata, to generate metadata that describe the identity, the state of the person, or anomalies like fall down or bad posture or low attention, for example, which is very important in the car, for example. Okay. These signals with metadata then goes then to the gateway and then to the cloud, where there is a high-level analysis of this data to classify the behaviors of the person on different temporal scale and decide if there are some actions to be done or some interventions. Okay. So the gateway executes a first analysis of anomaly detection signals that came from sensors, from intelligent sensors, and execute a diagnostic on the basis of data that came from other sensors, ambient sensors, or sensors without inside the CPU. And the gateway is the gateway between sensors and analytic algorithms in cloud. Okay, can communicate using Bluetooth or with sensors and through LTE with the cloud. Finally, the third level is the more complex level from the algorithmic point of view, is an analytic module which is in cloud, and it has a fine-tuning analysis to define the range of normality, so that if the signals coming from the persons are outside this range, then there is an anomaly detection. And okay, communication part. So the main motivation was that the current applications are more connected than smart, and it's we need to do a step forward to add smartness, artificial intelligence to the applications, and make our application connected and smart. Now, some of the experiments that we have done in this laboratory are based on the contributions of the different partners. STMicroelectronics contributed mainly with hardware, for example, with this artificial intelligence watch based on neural networks that are directly in the chip of the watch, that can, for example, be used to detect fall down of persons, and then also on this sensor tile board. AZIRTCOM contributed with the communication systems. This was a 4G. Now we can go to 5G systems that allow us to realize a cellular network LTE. Now is in the laboratory of the University of Milan Bicocca, with a small cell node that grant access through radio signals in mobility of devices, and the connection 4G LTE or for communication. That's, okay, these are technical data, and then okay, this is the hardware devices. Okay, anomaly detection. This is an example, a detection, fall detection with using smartphones. This is based on the analysis of the signals, different signals through neural networks. We have here essentially there are three of this, artificial intelligence watches. And the analysis of the data coming from them allows to recognize, to have a fall detection, fall down of the person. Even this, you see, on board there are accelerometers, gyroscopes, and different kind of sensors inside this chip. On the University of Pavia, worked on part of the analytic algorithms, essentially based on deep learning, embedded deep learning, while University of Milano Bicocca, in particular the Vision Lab of the University of Milano Bicocca, developed this Ambrogio home assistant that senses, sees, hears, and interacts with people. It is AI-based, and now we could try to integrate this with Chat GPT, maybe. Okay. So this is Ambrogio has a recognition module that is able to recognize the face, the voice, the faces of parents and friends, and detect faces of unknown people. It's able to recognize basic face emotions and to classify them, positive versus negative emotions, energetic versus passive emotions, and can carefully describe the faces of unknown people in terms of facial characteristics, age, gender, hair, and so on. Going to the action, not only to the face recognition, Ambrogio has an action recognition module that recognizes basic full body actions and can detect anomaly actions. He recognizes simple gestures associated to commands and can recognize audio commands and recognize emotions on the basis of the voice. So this has been applied on the magic mirror, on the automotive, and on the sofa television set. That are the three scenarios we have developed. So this experiment has allowed to focus on enabling technologies. As I said, the goal was not to develop specific products or services, but just to experiment ever with some level of freedom on different technologies, different approaches, and to stimulate cooperation between the different actors. And from this point of view, I think that the project was a success, and because it has increased the knowledge of all the actors involved. Thank you for your attention.
Professor Mauri, for your very complete review of these technologies and your experience. I just want to put you a few questions about your experience and what's the role, if you ever try to evaluate the role, the importance of gamification in this kind of researches of other people.
What do you intend by?
The way in which you can, you can provide physical activities or experiment concerning the path, the movements path, including sensors in a way that simulates games. So the usage of games of an involvement similar to the one that you can have using, for example, a computer with a video game for for training people or conducting this game. Okay.
Yeah, this I think this could be a further scenario to to explore, because we explored the three scenarios we've seen, but obviously you can add. This is any other scenario you want, and any other kind of sensor you are interested in.
Okay,
this general scheme.
Okay. And what's the importance of, as you can see, frugal technologies, so cheap technologies like smartwatches and so on? Yeah. Are they reliable enough for these purposes in your experience?
Yes, for obviously, if you have to go to the diagnosis of cardiopathies, or you need more reliable devices, but okay, obviously for a level of remote monitoring of conditions, anomaly detections, or critical situation detection without going to depth into the diagnosis, I think you can find low price and tools, devices with the right level of confidence and quality.
Okay, it's clear. Thanks again for your very clear speech of this such wide scenarios of possible application, and of course during your long expertise of this kind of training in order to rehabilitate, to recover, and to study different parameters through the acquiring of vital parameters, of course. And so we can check the situation about the availability of our speakers in this section. The second speech is from Professor Bai from the Telemedicine Society of India, but maybe is not still connected.
Yes, sorry, Matteo. Professor Bai asked me if it's possible to speak after or tomorrow morning. Maybe because I have some problem of not of connection, because he is employed in another activity. She asked me, Professor Bai is a woman. She asked me to speak maybe tomorrow morning at noon and at the end of the Italian session.
All right.
I want to thank Giancarlo because this project is very interesting. I think, Giancarlo, this project application of this results of this project can be useful in alert system in our activities for people, aging people, elder people, or disabled people at home for some problem to get the medicine, the drugs, or other activities during the stage in house or in the car. But it's possible to extend this system to control, to activate some device, mechanical device for rehabilitation, some robot.
Yes, yes.
Robotic system in order to activate this mechanical or mechatronic system for start some exercise for rehabilitation of the lower on the upper limbs, for example.
Yes. This is the fourth step in our loop. We have sensors, communication, cloud, what you want, analysis, and decision that can be also the activation of a new device, of an actuator device that can do also mechanical actions or to activate a caregiving robot that gives the pill to the patient that has forgot to take its pill and so on.
Nice. Thanks.
Perfect. Okay, so Francesco, if you agree, we can go on with the next presentation from Luca Neri. And Luca Neri is a doctorate student in Johns Hopkins University. Is under the patronizing of Professor Borghi in Sant'Orsola Hospital of University of Bologna. And of course, there is a topic of paramount importance in, in relevation of parameters and telemonitoring, which is based on the wearable devices. And Luca Neri, he cannot participate directly due to the time difference. But anyway, we have a recorded presentation from Luca Neri when he is talking about these particular wearable devices made of textile sensors, so not metallic sensor, but textile. It's a new approach on this topic of the wearable devices, and we can see something about the project implementation, the board of experts taking part in this project, and also the application about artificial intelligence and deep learning over the acquired data set. So let me open up the presentation.
The research team that contributed to this work is composed by myself, my PhD tutors Claudio Borghi, Henry Halperin, Matteo Berdier, a medical doctor Aravindian Kolavendulu, and one student Sojic at Johns Hopkins Medical Institution. And for Accurate, the CTO Gianangelo Gemignani, the software developer Antonio Augello, and the tech advisor Matteo Botteghi. Wearable devices are becoming increasingly present in everyday life. The increased rate of population aging and the high healthcare costs, coupled with the development of new sensor and artificial intelligence algorithms, are guiding this innovative technology. In the last 5 years, the research efforts in this field have exponentially increased. And despite this impressive trend, the development of new wearable devices face some challenges, as the battery life, limited computational resources, data reliability, usability, comfort, data protection, and privacy. Considering all the opportunities and challenges, our research group is developing a new smart t-shirt that will work within a novel telemedicine infrastructure, capable of monitoring different biosignals and aiming to create a user-friendly device with reliable algorithms. We are focusing our initial efforts on developing algorithms to analyze one lead ECG signal to evaluate and alert the medical personnel about diseases such as arrhythmias, hypertrophic cardiomyopathy, and sleep apnea. This algorithm prioritizes result accuracy and computational efficiency, mainly because mobile devices are resource intensive, usually running multiple applications simultaneously, and have limited ability to perform real-time monitoring. The first test demonstrates the potential of this smart t-shirt and the need for continuous development of new algorithms and features. If we consider the use of wearables for the cardiology monitoring applications, they fit into a new category of devices that with different characteristics compared to the devices currently available, that they can range from the classic standard 12-lead ECG, where the signals are recorded for 10 seconds, to the expensive and invasive implantable monitor that permit to record the signal for 2-4 years. The smart t-shirt that we are developing has different and interesting characteristics that permit to record the one lead ECG with real-time analysis for months. It is also very comfortable and inexpensive. These characteristics are generally leading the success of wearable in the present and the future healthcare. Together with our industrial partner at Accurate, we have focused our work on 4 different areas. We developed smart t-shirt and smartphone app prototypes. We developed and tested our QRS complex detection algorithm. We are preparing studies to collect data and signal to analyze the performance and improve our smart t-shirt and its algorithm. We are evaluating the state of art of the use of artificial intelligence and machine learning in wearable applications to develop new algorithms for detection and prediction of diseases. We have developed a new smart t-shirt that is essentially a crop top. This decision has been made considering the feedbacks from the users and patients that prefer the crop top solution to the entire t-shirt that we developed last year. The smart t-shirt is based on polymer-based sensor directly integrated on the t-shirt fabric. The last model has a smaller control unit and its battery lasts up to 36 hours. It is washable up to 30 times. The main signal that we measure are one lead ECG and the respiration signal. We have also additional sensors as body temperature, SpO2 that we can read through an external device that communicates with the control unit, an accelerometer, and a gyroscope. The smartphone app has different sections, and we can start and check new monitoring sessions, visualize the ECG signals and the respiration signals in real time, manage the record and monitoring session and send them to the physician, and manage the app and the t-shirt settings. The monitoring sessions are also saved on servers to permit the access to medical doctor and for additional analysis. For example, evaluating long sessions with machine learning algorithms require high computational effort that can be overwhelming for the mobile resources. We developed our QRS detection algorithm for the ECG signals that is a modified version of the gold standard Hopkins algorithm. We needed to develop a new QRS detection algorithm to decrease the processing time and making our app faster for the real-time analysis. We use 6 different datasets from databases on PISMET and on Harvard website. The datasets are ECG signals with different characteristics: high quality, low quality, normal sinus rate, arrhythmias, pace rate, and signal recorded during a telemedicine project called Telehealth. These datasets have different characteristics based on the studies that generated them. Comparing our solution with the gold standard algorithm, that is the Hopkins algorithm, we obtained improved accuracy and F-score and reduced processing time. We wrote the code in Python, and the results are displayed in these two graphs. We have an overall improved accuracy and F-score, and we have an important difference in processing time that make our solution more efficient, in particular for the use of wearable and mobile devices. In addition, we are also implementing existing algorithms developed by other research groups to test the performance on our solution, on our smart t-shirt. We are focusing on three main areas: arrhythmias, sleep apnea, and mental stress. The idea is to find the computational efficient algorithms for wearable application, and we are mainly evaluating algorithm dataset from three different sources: Physionet, GitHub, and Kaggle. We are also working to get our dataset and use them to develop and test new algorithms and new artificial intelligence algorithms. And here we can see the three main projects that we are preparing and implementing to collect data and have our own datasets. This gives an idea of all the data collection process required to have our own data to develop new solutions, and in particular artificial intelligence algorithms. The first study at the Sant'Orsono-Pighi Hospital in Bologna consists in a comparison between the ECG signals and the related parameter recorded and calculated with the smart t-shirt and the ECG signals recorded with a standard Holter ECG, and also the parameter recorded with a smartwatch. We have received the approval from the ethics committee in April, and we are currently waiting for the new Holters and software to start our study. We expect to start the project next month. The second study is a part of a collaboration between Accurate and the Italian Red Cross, and the employees of the Italian Red Cross will wear the smart t-shirt for a set number of days in a month, and this study is expected to enroll 100,000 volunteers in the next 12-14 months. The target of this study is the evaluation of monitoring capabilities of our smart t-shirt during work activities and the detection of arrhythmias and sleep disorders. Here you can see the smart t-shirt that has been designed for this study. The idea is to combine our smart t-shirt with the standard garment of the Italian Red Cross. The third study has been submitted to the ethics committee of Johns Hopkins Hospital to have access to the patient records, to evaluate and develop artificial intelligence algorithms capable to detect and predict cardiac disease and sleep apnea. We are also preparing a second request to submit to the ethics committee to include in our research the data from the study between Accurate and the Italian Red Cross, and to test the smart t-shirt and volunteers here at Johns Hopkins Hospital. As mentioned before, we are evaluating the use of artificial intelligence and machine learning in wearable devices. To do that, we are preparing a review paper, temporarily named Application of ECG AI to Wearable Devices for Disease Detection and Prediction. We have performed our research with keywords on Web Science, PubMed, and Scopus, considering the manuscript in the last 5 years. The number of papers on this topic have grown exponentially in the last decade, and the number of papers in the last 5 years are more than 50% that all papers that have been written on this topic in the last 80 years. So it is a very hot topic now, in particular the application of artificial intelligence to the ECG from wearable devices. The main diseases considered in this paper are arrhythmias, as AFib, cardiac arrest, mental stress, COVID-19, ischemic cardiomyopathy, myocardial infarction, sleep apnea, hyperglycemia and hypoglycemia, and much more. For the application of machine learning algorithm, we are considering the entire data mining process that permit to develop the best algorithm for each particular application. In fact, the machine learning is not limited to the training and test of different models. It actually requires a long and important process of data selection, collection, understanding, and preparation. And the machine learning algorithm performance is very dependent on the data used to train it. Example of models used in medical application are supervised machine learning. Example are linear regression, support vector machine, decision tree. Unsupervised machine learning, example are a priori, k-means clustering. And the promising supervised deep learning as convolutional neural network and recurrent neural network that are very popular in the last year in the field, in particular in the application to ECG signals. In this slide, we can see the main differences between the traditional machine learning methods and the deep learning methods. In the traditional supervised machine learning method, it is required the extraction of features and expected output from the ECG through the knowledge of medical doctors. For example, the medical expert chooses the parameters of interest that should be extracted from the ECG to detect a particular disease. For example, the characteristics of the P wave of the ECG are very important to detect and analyze the atrial fibrillation. The extracted features and expected outputs are then used to train the machine learning model that work as classifiers, and they learn how to detect the disease based on the data that we use to train them. The deep learning methods are different. They process the raw ECG data and they identify the output, learning from the input without the supervision of medical expert, as we have just seen with the traditional methods. Based on our literature review, the deep learning method are the most used in the last years for this application. For this reason, our first test will be concentrated on the use of deep learning methods. And considering the fact that machine learning and deep learning models require a huge amount of data to be trained for specific disease and application, we are currently evaluating the use of a technique called transfer learning. And we use the available dataset on Physionet that has been used by most of the research group to train deep learning algorithm to create the first model. Then the model trained with this data will be further developed and trained using our dataset collected with our smart t-shirt for the same diseases. In this way, we can train a dedicated deep learning model for our application and for a specific disease without having huge amount of data with our device. So, considering all this presentation, the takeaways are there are great opportunities in these fast developing research areas. Wearable and their features are expanding their presence in the daily life. And the main target is to monitor biosignals with the aim to detect and predict possible diseases in a fast and reliable way and improving the life of everyone. For sure, as we see, we've just seen with this project, with great opportunities comes great challenges and obstacles that we can essentially divide in three categories. The physical device with the battery life, computational resources, design, comfort, and usability. The data, they need to be reliable and need to guarantee protection and privacy. The algorithm with artificial intelligence and in particular machine learning and deep learning that need to be developed with the right data set to avoid outcome errors, and they must be computational efficient. That's all. I'm available for your question.
Okay, that was a very good example in which we can see an innovative technology that represents the habilitating elements for new kind of experimentation and training. The presentation was talking about the Italian Red Cross experiences and the telemonitoring project currently in these last months reached 7,000 volunteers of Red Cross constantly monitored by this solution, this wearable device. It means more than 1 million hours of recording parameters till today. So in this moment it could be the most important data set in the world considering ECG parameters. So it's really important having new technologies that could be affordable and also easy to use to be introduced in the practice of experimentation and everyday life usage. So, but let's check again our speakers. So Professor Kinkorova is not connected currently. And also,
Aleksandra is present.
Yes, we have.
She's present. Oh, okay, Aleksandra, if she wants.
Perfect. So, Aleksandra Sojic from ITB-CNR of Milan. If you are ready, you can. Perfect.
Today I'm going to present some reasons for the need to have a human time frame ontology. And I will refer actually to something that some of the previous speakers talked about related to sensors and collection of information from various sources. And based on that, I will also argue why we need yet another ontology, but that should simplify our way of recording, collecting, and analyzing data. Okay, so basically, I will introduce to some people who are not very much familiar with the ontology, computational ontology, and just briefly address some of the needs related to formalization of knowledge based on ontology from various fields, such as ambient-assisted living, use of sensors for healthcare, wearables, and epidemiological and clinical service. And then I will show how time is represented in this domain and why we need human-centered representation of time-related data. And then I will briefly show some of the key classes of human time frame ontology. And I will really appreciate you if you can give your feedback from your own experience with collection of data from sensor service and clinical studies, because this is part of an initial work that we intend to deploy in our epidemiological and other clinical studies. So ontologies are explicit specification of conceptualizations, meaning that they represent concepts in an explicit and intersubjective manner. So it's not only about having standardized definitions, but it's also about having community who will agree on how to explicate and how to use some terminology. So this is particularly relevant for the domain of digitalization, where we expect to have possibility to exchange information across distributed systems, across sensors, across cloud platforms, clinical data, and also to enable understanding across different communities and users. In this domain, terms are used as labels for concepts, but on that very light level, we speak about reference dictionaries that are very often used, and there was a huge effort in biomedical community in various numerous domains to define these precise dictionaries. But beyond dictionaries, when we speak about some higher level of formalization and about real ontologies, where we also expect to have something like artificial intelligence applications and automation. We also speak about explicit definition and formalization of relationships that stand between these concepts. So we use formal language to represent these relations and to tell to the machines how to reason about these concepts. So basically following some analysis based on human cognition, biomedical reasoning. In this, when we speak about this formalization and formal ontologies, we speak about universe of discourse that we have to define to be very specific and to where we use shared vocabularies and relations that are defined and formalized within the target segment of the world. So basically, these are some of the key concepts where ontology engineers have to consider while formalizing and specifying this language. So when we speak about ambient-assisted living, wearables and sensors for healthcare, we speak very much about complex systems. You have seen some of the examples. We often, because we speak about human health, we speak about three high-level domains that can be target of sensors and identification of information that can be collected, formalized, and analyzed. So we speak about possible sensors that target person, physiological states, behavior. We speak about sensors for environment that can track information coming from environment, that in epidemiological terms is labeled as exposures. So some of these exposures can be like air pollution or fresh air or certain humidity or temperature. But some exposures can be also more closely related to personal health states. For example, people with some diagnosis or health status that can indicate some problems in their metabolism can have high cholesterol. So in this case, even if it is a feature of a person, it will be also be exposure because human system and certain organs will be exposed to high level of cholesterol that eventually can lead to certain diseases other than like this level of cholesterol and so on. So basically, like employment of sensors and digitalization of this collection of information to understand personal health status is widely spread, and very often it's spread not only and used not only like to monitor like disease related parameters, but also like behaviors such as physical activity or recording information about nutritional behaviors and stimulating maybe and motivating people to adopt healthier lifestyles and eventually to intervene on their health status. But this is definitely a huge domain with very complex information that we talk about. And we talk about some numerous external environmental exposures, but also like specific exposures related to, as I mentioned, like sleep behavior, diet, drug consumption, smoking and alcohol use. So here on the left-hand side, you see just a brief sketch of several parameters that can be tracked and measured by sensors related to external exposures and human behavior. On the right-hand side, you see a figure by Peters and colleagues that represents the common risk factors. Like its figure is created based on several meta-analysis and reviews from the epidemiological literature, pointing to the key risk factors that impact the major non-communicable diseases. And in particular, on the top, you see like unhealthy diet, physical activity, smoking are the health-related habits that very much impact non-communicable diseases. And in some studies have been shown, in numerous studies have been shown that even more than 30% can be development and high prevalence of diseases such as neurodegenerative diseases or cancers, especially some types of cancers, are highly associated with unhealthy behaviors. And that's why many public health studies recommend and suggest that interventions are focused on unhealthy diet, like interventions on reducing and modifying unhealthy diet and motivating physical activity and eliminating some unhealthy habits. So basically, like our institute and my personal experience in several European projects have actually shown very good results in using sensors to track and intervene, track human behaviors related to physical activity, diet, and intervening to motivate healthy lifestyles. But in this presentation, I'm not going to talk about these interventions. I'm just going to talk about certain aspects of collection of data. So basically, since we deal with a huge amount of data when we speak about lifestyle habits, we speak about heterogeneous information and heterogeneous research interests and targets and interventions and aims. We speak about different instruments, different service, digital or pay, always more and more used digital service, collecting information about habits, human habits, then sensors, different sensors coming from different manufacturers, and different data coding approaches and modeling approaches. But luckily, we also have on the other side a very important need to integrate this data coming from multiple studies, coming from multiple resources, trying to align this data to make them interoperable and to be able to provide even stronger evidence about association of disease and certain behaviors, and also about efficiency of certain interventions in order to provide recommendations for public health. Luckily, like since these efforts towards alignment, interoperability, integration have already provided and resulted in numerous standards for data specification, collection, management, data coding, data representation analysis. Just to mention some of them, like Health Level 7 standards, FAIR, DICOM standards for representation of imaging, and a FAIR principle to provide like a motivating researcher or even obliging researcher, like for that are funded from public fundings, to provide like results to research results to make them findable, accessible, interoperable, and reusable. So that's why like considering all these, like ontologies are one of the best way to make data findable, accessible, reusable, and interoperable. But unfortunately, like my own experience and also literature reports about research projects and studies, that very often when it comes to coding, even semantic-based coding, for practical reasons, programmers are not able to implement, or maybe some of them are not even aware of importance of use of standards and standardized ontologies. And they approach to coding and formalization of information in pragmatic way that sometimes results in a classification as this one that you see here, that is from Borges and Ludger Jansen. You can see his interpretation, very nice representation of his article from 2009. So classification of animals, like, and in this example of classification, you can see all examples of what people shouldn't do when modeling data from some domain. I will not go now into all details to analyze why numerous of these, what kind of mistakes we see here, because you probably have met already this classification. But just to mention, for example, in this classification, there are a mixture of different levels of categories, like meta classes, like classification based on different criteria, all put together, like putting together like unbound animals, trained animals, mermaids, fabulous creatures, others, that is the kind of category where you put everything that you don't know where to classify. So basically, it's an example of a bad classification that is very good for training purposes, and every computer scientist working with data should study carefully errors made in this classification. But what principle of good classifications are actually to consider ontological grounding, to consider if you are classifying dynamic objects, static objects, changeable, if your structure is well defined, if you have disjoint classes, if your classification is exhaustive, no ambiguity in specification of your classes, it's uniform and precise. There are no mixtures between meta types, like representing data and metadata on the same level. But in any case, when we speak about implementation of this classificatory principle in data modeling, we have to be aware of that epistemic and pragmatic reasons actually drive very much and motivate how we implement this classificatory principle to model domain data. And in some cases, it's very, very clear that it's not easy. It's not easy at all. And some standards sometimes cannot help because there are many standards, but when we deal with real cases, like for implementation of and integration of sensor data, we have to deal with many levels of complexity. And in particular, time-related information is something that I would like to tell you something about today. When we speak about time-related information, we speak about persons who in epidemiological service or clinical assessments, or in sense like collection information via e-diaries and similar platforms. Even when we speak about programmers who collect data from sensors, they think in terms that are human terms, like human perception of time. And that's why we need to consider how to model this time-related information that will capture like human behavior, physical activity, sleep behavior, drug use across different time frameworks. Also collect information from Fitbit and similar sensors. So when we speak about existing standards for time representation, we have already some recommendations, and some of them for example, this is World W3C recommendation of time ontology in OWL. It's very detailed, like a representation that can be used to represent time-related information. It also addresses some of the issues related to ISO standard for temporal representation. It contains like 21 class and a huge, like 58 properties, data properties and object properties. And it's very detailed about possible relations between time periods, using even like 13 elementary possibilities that time points can relate them, representing time points relations. However, if you go to see this recommendation, you will see how detailed and well done, developed it is. But it's actually missing something that is very important for biomedical studies. So this representation of time point, like concepts, is actually missing like a human perspective. Because when we speak about epidemiological and clinical service, we speak about humans who report about their behavior, either in digital service, paper forms, or in various diaries and apps. They report about their lifestyle habits, activities, and they do that the same way they think about it. In terms of a natural language, the true an ontology formalization may also be machine readable. And like epidemiological studies that are cross-referenced, that we need to develop any recommendation for public health relevant. These studies also use this human-centered terminology in service, in the collection of data from sensors. And they also contain precious informations that deploy this terminology, talking about observed behaviors and scientific evidence of intervention effectiveness. And if we want to make our results of scientific study replicable or reused in different studies, then we have to try to align these studies also respect to time points that they refer to. So data collected and structured within a human time frame makes sense also from a behavioral and biological perspective, and I will show you briefly why I say that. So basically, based on empirical data, like coming from personal experience and also from review of the literature, we try to capture time frames that are used for personal and scientific purposes in scientific discourse, to extract the top level categories that can be reusable and enable to collect information from heterogeneous sources, like including sensors and service, to facilitate interoperability across the studies. And this model is developed by making a kind of fair trade compromise between classificatory perfection, trying to be as complete as possible, exhaustive and coherent, but still lean enough to enable application in real, real applications, not just having it as a nice theoretical concept. So that's why it's very light in AL profile model that can be expanded with other relations and other concepts that, if needed for some decision support systems design. It can be interoperable with other standards, such as semantic sensors ontology or time ontology, and can be a kind of bridge or mid-level model between W3C time ontology and real-world research data collection. So basically, these are some of the top-level concepts that are day, time frequency, activity time, day period. And when I show the classes here, it will be even more clear why why we have these concepts classified this way. So basically, why we need this classification. So when we speak about human habits, like all people who work with sensors and trying to collect information about human habits or in epidemiological studies, we know that behaviors and human habits very much vary in different time frames that are represented in terms of week, such as weekend behavior is very much different than weekdays. So like your bracelet will tell you also the same. So some people are more physically active in weekends, some others in weekdays while they go to work and they commute or they do some other activities. Then we need to consider season. It's another time frame, human time frame category, because human behaviors like nutritional and physical activity very much differ in different seasons. And these differences should be considered also when analyzing data, when collecting data about human behavior. Another activity, like a very high level of specification activity time, such as meal time, physical activity time, leisure, work time, and sleep time, that definitely impact information that we collect because it will change in different activity time points. Then definitely we need date, and we need, in some cases, just timestamp, in some cases, like just year or just month, depending on the type of the study. Then we need to consider the day period, such as if information is collected in the afternoon, evening, if habits take place in the afternoon, evening, if medicine is consumed twice, like in the morning or in the evening, and so on. Because it will also impact interactions, for example, with meals, and also like other parameters that can be relevance. Time frequency categories that we have to consider as our calendar frequencies, such as if activity takes place or habit takes place daily, weekly, yearly. Relative frequency, like if you work with epidemiological service and clinical assessment, so this is information relevant to consider, and often information is communicated as always, never, often, sometimes. And in some cases, it will be helpful also to specify a time frequency number, for example, daily, twice per day if you take a medicine and so on. And time points, like if we want to consider start point, end point of clinical study, or if we want to consider time point, end point of some habits such as smoking. And finally, we have this categorization of lifetime period that basically summarizes like the key stages of human life, like from newborn period, toddlerhood, childhood, adolescence to late adulthood. That like in older age, we have like a 10 years interval that definitely can be even more fine-grained if needed for research purposes. So basically, thank you very much. And I hope that you can give me your own perception from your own experience, like what is your experience with time-related information? Which classes from this ontology you think we should improve or add or remove? So I will give my word to you. Thank you.
Thank you. Thank you, Aleksandra, for your great contribution on this field, so particular field. And there are any questions from the audience?
Very nice presentation, Aleksandra. It's the first time to apply ontology systems, ontology web language to the data coming from the sensors, because this kind of data are very, very heterogeneous.
Yeah, we actually did apply ontology in an indirect way in some European projects, actually using sensors to intervene like on health behaviors. But based on that experience also, among others, I understood that actually we need something that refers to time frames in like this human-centered way, because otherwise people keep creating their own categories because the existing standards are not sufficient.
It's possible to use this kind of technology, of course, ontology and sensors in a neurological disease, in cognitive impairment disease.
Yeah, from my point of view, it can be applied in very numerous domains, also like tracking behavior related to like neurological problems, like monitoring activities or even adherence to therapy, for example. Yeah, definitely, it's so simple and try to like attempting to be lean in order to enable application across different domains.
Thanks.
Okay. Thank you.